Hi, this is Sajid. I'm going to discuss about how machine learning can be used for building a system for detecting international roaming fraud. Here, we are going to check the roaming fraud detection overview. Then we'll move on to the fraud challenges and fraud exploitation methods. Then we will introduce the machine learning detection and the data source that we are going to use. First of all, let's start with the opportunity evaluation. International roaming fraud is a significant challenge for telecom operators, resulting in substantial financial losses and customer dissatisfaction. Fraudsters exploit roaming agreements and billing delays to make high-end calls or data usages that go undetected until it is too late. This presentation introduces a machine learning based system designed to detect and prevent such fraudulent activities in real time. By leveraging large volume of call records, usage logs and location data, the system aims to identify suspicious patterns and alert operators before damage occurs. But before moving ahead, let's see why machine learning is suitable for roaming fraud detection. Roaming fraud detection is an alternative use case for machine learning due to three key criteria: value, feasibility, and impact. The problem is valuable to solve because it directly affects revenue and customer trust. It is feasible because telecom operators collect a rich data set including CDRs, location data, and device metadata. Machine learning is impactful in this context because it can detect subtle and evolving fraud patterns that traditional rule-based systems often miss. Additionally, machine learning enables real-time decision making, which is critical for preventing fraud before it escalates. Now let's analyze the CRISP DM methodology for step-by-step designing of machine learning system. As a CRISP DM step 1, let's define the problem and the success metrics. The primary business objective is to detect fraudulent international roaming activities in near real time to minimize financial loss and protect customers. Success will be measured by outcome metrics such as reduced fraudulent related losses, improved customer satisfaction, and faster fraud resolution. Output metrics includes model precision, recall, F1 score, and alert latency. Relevant factors influencing fraud detection includes call duration, destination country, time of call, user location, device ID, SIM change history, historical usage patterns, roaming partner network, and billing anomalies. These variables will help build predictive models that distinguish between legitimate and suspicious activities. So step 2 of CRISP DM, let's do the user valuation strategy. To validate the solution concept, the strategy involves engaging with fraud analysis and telecom operations teams to understand their pain points and expectations. A pilot version of the model will be deployed with shadow alerts that do not block calls but flag suspicious activities. These alerts will be compared with actual fraud reports to assess accuracy. Feedback from users will also be collected to refine the model and improve usability. This iterative validation process ensures that the system meets operational needs and delivers a reliable fraud detection. Now let's go to the machine learning system design. Here we're going to select scalable cloud architecture. The system uses cloud deployment for centralized data processing and global integration because we might be selling this product to multiple telcos. And since the data is huge, we are going to do the offline training models. And we also make sure that online interfaces are enabled for users to take real-time action based on the real-time fraud detection. And also it will be connected to the external data through APIs like uh, uh, operator billing systems or call record databases so as to get data for training the uh, ML tool. Now let's discuss what is the production risk. In production, we may have concept drift as well as data drift. Concept drift will occur when fraud tactics evolve, making historical patterns less relevant. Data drift can result from changes in roaming agreements, pricing models, or seasonal travel patterns. These shifts can degrade model performance over time. To mitigate this risk, the system includes continuous monitoring of model metrics, scheduled retraining on fresh data, and drift detection mechanism using statistical tests. A feedback loop from fraud analysis is also implemented to refine the model based on the real world observations. In summary, the ML-based fraud detection system offers telecom operators a proactive and scalable solution to combat international roaming fraud. By leveraging rich data set and enhanced pattern recognition, the system can identify suspicious activities in real time, reducing financial losses and enhancing customer trust. The architecture supports continuous improvement through validation and retraining, while production risks are managed through robust monitoring and feedback mechanism. Overall, this solution represents a significant advancement in fraud prevention for telecom industry. Thank you.